All right, good afternoon. So today I'm going to be presenting a talk about the most recent rupture of the Thousand Lake Fault post last glacial maximum, examining rupture length and average displacement using southern Utah's uh, recent LiDAR data. And so in this slide, we're looking at the Thousand Lake Fault, or along the Thousand Lake Fault. To the south is Boulder Mountain, which is a relatively flat-topped mountain over 10,000 feet tall in south central Utah. And the Thousand Lake Fault runs along the west side of this mountain. And actually, we can see some expression of the Thousand Lake Fault and how it's juxtaposing displaced tertiary volcanics against Mesozoic sedimentary rocks in the foreground. And then I've got a couple of arrows there that are showing a couple locations where we found expressions of quaternary faulting in kind of reconnaissance studies as I was teaching geology field camp for Utah Valley University here over the past, I guess, nearly a decade now. But in 2018, we did a paleoseismic trench, and since that time, the 2020 Southern Utah LiDAR became available. And so we had opportunity to mingle those data together and really know something pretty significant about the details of the last rupture, the most recent event here. And so this work is done by myself as well as David Johnson, who did most of the work that I'm going to present here today about mapping in the LiDAR, that most recent event. And then other co-authors related to the study are shown as well. Okay, so the Thousand Lake Fault lies along the boundary between the Basin and Range and the Colorado Plateau physiographic province. And so the escarpment, if we look on the right of this image, kind of goes along Boulder Mountain here in black. I've outlined the major escarpment or break in topography. And to the north, the Thousand Lake Mountain itself. This escarpment is aligned with continued faulting, which moves to the south and west of Boulder Mountain, and then additional faulting kind of between the Thousand Lake Fault and the Fish Lake Graben up to the north and west. And these traces of faulting continue further north and seem to align with the Joes Valley Fault and other such structures. So yeah, we're at the very edge of what we call the Great Basin and the Colorado Plateau. And in fact, we are at the drainage divide basically between that. And so this, the drainage of this watershed that's shown here on the right for the Fremont River flows into the Colorado River, but every other drainage to the west of that flows out into the Great Basin, is internally drained. We can tell something about the activity of this Thousand Lake Fault in that the incision of the Fremont River is able to keep up with uplift along the fault, because the fault, you can see it's uplifting the Colorado Plateau or the east side of the topography and down dropping the valley over here to the west. And so the fault is not moving up as fast as the river is cutting down. Okay, so prior information about the Thousand Lake Fault. So the Quaternary Fault and Fold database of Utah, when I last accessed it, said that it had activity since the last 750,000 years, so since the mid-Pleistocene. And that's due to faulting of river terraces that have formed since the start of the mid-Quaternary. And then Marchetti, one of my colleagues in 2007, had mapped some of the landslide deposits on the primary escarpment of Boulder Mountain. So just to the left of that southern box. And there, not too much was seen in those landslide deposits, but this was prior to LiDAR. So he said those landslides deposits were undisturbed by faulting. And And so we can constrain the last activities to sometime more recently, or sorry, older than 125,000 years ago. Yeah, so I've been long curious about this fault driving to the Colorado Plateau and our UVU Capital Reef Field Station. So I wanted to study this more, and so I started taking the UVU field camp class there and mapping, especially in where the middle box is. Um, just looking at the topographic data that we had at the time we started back in about 2015, you can see that the fault length is about almost 50 kilometers. And the slip rate data from the Utah Quaternary Fault and Fold database, this is less than 0.2 millimeters per year. And so it started to ask the question of what more can we say? And so in this talk, we're going to briefly touch on long-term displacement and what that says about the slip rate aligned with the Utah Quaternary Fault and Fold database. Then we'll show briefly the 2018 paleoseismic trench, which has OSL dates associated with it and constrain something about the timing of the most recent events on the fault. And then we'll show what the 2020 LiDAR data informs us in terms of relative activity with quaternary surfaces up in this high topography. So here's the Thousand Lake Mountain. So we're looking to the east, and I've highlighted the major escarpment of the Thousand Lake Fault in red with a down-dropping arrow there. And at the top of the Thousand Lake Mountain, you can see it is a flat top mountain. It's volcanic rocks. Those are dated to about 24 million years old. And same rocks can be found out in the hanging wall of the valley on the far west side of the valley. As you dip back, as those rocks dip back towards the mountain front, you can see that there's quaternary fill and river fill associated with faulting and fluvial activity along the Fremont River. Fremont River flows to the right of the image. And so we have a pretty good displacement marker with these 24 million year old volcanic rocks. So doing just some simple projections, I estimate about 1,200 to 2,500 meters of displacement across the Thousand Lake Fault with those 24.5 million year old volcanic rocks. If we assume a tectonic initiation with a wide uncertainty of 10 to 16 million years old, that gives us a minimum long-term slip rate of 0.08 millimeters per year and a maximum of about what the Utah Quaternary Fault and Fold data says of 0.25 millimeters per year. Okay, so zooming in to think about more recent studies, the paleoseismology. So the field camp mapping area where I've been taking students is located within Beek's 2016 mapping area. One of the reasons I chose this area for taking my students is because there is pretty good expression of quaternary faulting here. Also somewhat complex fault zone, gives them some geologic puzzles to study. Of course, also, when we started in 2015, there was no good map of the area at the time. It was a black and white raw map. But Beek's map is there now, so hopefully the students aren't looking it up while they're in the field. So we dug a trench there in 2018, and we dug it on this alluvial fan coming out of this drainage in the middle here. This drainage is and this fan are beheaded and no longer active today, but we can see a prominent lineament in the air photo. Actually, several lineaments coming across the fan showing evidence of faulting, and those are mapped in the 2016 Beek geologic map. And then on the right, we can see a hillshade map of and contour map, and those lineaments are showing up in there as well. And so we dug one trench, that's all we had money for from an internal grant, across the most prominent of these lineaments, shown as the yellow line there near the arrow. I also drew a topographic profile here for you to see the expression of faulting through the region. And so the paleoseismic trench was dug across the western or leftmost of these topographic scarps in the alluvial fan. And so you can see the total displacement across the surface is approaching 5 meters since the fan was abandoned, which we think was on the order of about maybe 100,000 years ago or more. Of course, there's a little bit of uncertainties with the total displacement because of inflation and deflation of surfaces. There's a lot of dust in the fan surface, and also a lot of the fan is being held up really nicely by these really prominent volcanic boulders. So here's a picture of one wall, the south wall of the Thousand Lake Fault Trench that we dug. And so in this image, I just want you to focus on the soils primarily. And so we'll first look at the bottom here, and hopefully you can see on the left side that there's a fairly nice or slightly organic rich A horizon in the soil. And then below that, you can see some staining of white from a kind of aridosol caliche development. So that's really prominent above that top left yellow star. As we follow those soils to the right, I've tried to highlight where they are as we approach this fault zone, which is kind of highlighted in red here. And on the downdrop side, we can see that the soils are quite a bit lower. So indeed, we have cumulic carbonate soil across the fault scarp. And the detailed mapping of that shows us several things. So if you move up to the interpreted map, we see that we interpret it as a stage 3 BK soil on the downthrown side and the upthrown side. But on the downthrown side, we have another level of soil, which we say is BK 1-2 stage. And that is actually sitting under a wedge of colluvium coming off the fault scarp. And so my interpretation is that there's one young event associated with that colluvial wedge, and that there's some prior event that over-thickened that happened, during the time of that earlier soil development of the BK3 that thickened it. And so we interpret that there's two events since that BK3 soil was developing. And so we have several OSL dates. We have 4 OSL dates. 3 of them come from in the stratigraphy below the BK3 soil. And those all are older, ranging from about 50,000 years ago to over 120,000 years ago. And then we have one OSL date in the essentially the base of the MRE colluvial wedge, which is younger and dates to about 20,000 years ago. So the most recent event we would interpret happened more recently than about 20,000 years ago. And then there's a prior event, which we think happened between 20,000 years and about 50,000 years ago, based upon soil development over the top of that youngest age within the stratigraphy there. So 2 events in the last 50,000 years or so. Total displacement across the exposure of the trench of that BK3 soil horizon is about 2 meters. And so we interpret about 1 meter per event of displacement on average. Remember, this is only one expression of the fault across this fan surface, and there are several other traces. Okay, so now that you've seen the trench results, we'll back out and we'll look at the character of faulting along the Thousand Lake Fault in two other locations away from that central part where we're looking at the paleoseismic trenches in the middle box. So first we'll start to the south, where we can see clearly that there are fault scarps that are cutting glacial material, which are streaming off the top of Boulder Mountain. You can see the kind of scraping that the glaciers did across the topography here down the side of the slope and producing some moraines and other features there in the image. And then on top of that, there's these kind of debris fans coming off the escarpment and going out into this at the bottom of the fault scarp. And those debris fans are clearly cut by a fault scarp. And so don't have it here in this image, but I'll show you some profiles across there. Some profile lines are shown there. We can see some other scarps over to the left. And so these fault scarps, there's only a little bit shown here, but they're hundreds of meters long, fairly contiguous and continuous right here. So this is way up over 9,000 feet above sea level. To the north, along the primary escarpment of the northern Thousand Lake Fault, we do see another area where the glacial activity comes across the fault escarpment and fault zone. And we checked several other places, but this is like the most key place, I would say, in terms of clear, young geomorphic features. So the fault zone is outlined with arrows on both the top and the bottom of this image. And then you can see late last glacial maximum moraines coming across there. And you might be able to trick yourself into seeing some kind of deformation of there, but I don't really think you can be very confident in that. And so, I've profiled through there a bunch, and I don't see that the Thousand Lake Fault has appeared to cut through these last glacial maximum moraines here. And to the north of that, there's some areas where the fault scarps is mapped in yellow. We can't see them in the image, but these are not like, so the yellow scarps are ones that I mapped when I first started reconnaissancing the Thousand Lake Fault's LiDAR data that came out in 2020. And they're not discriminating between kind of very recent scarps and old scarps. And so here we don't see any recent scarps. So my student, who now is a grad student at Idaho State University, David Johnson, he's a great field geologist, quite a good GIS mapper as well. He took on the task of going through all of those fault scarps and identifying which of those scarps represent displacement in the most recent event. And so he profiled through all the scarps that he found and followed them and found those that had significantly steep slopes, and he interpreted as had either Holocene or very latest Pleistocene activity. And so where he identified recently active fault scarps are shown in red, solid lines on the map on the left. And so we can see that the most recent activity along the Thousand Lake Fault to the south on Boulder Mountain is actually right up near the top of the mountain. In some cases, it is within the volcanic plateau up there, in actually most of the cases. As we come to the north side of that tip of the mountain, we see maybe some evidence of escarpments kind of down into this kind of debris, glacial outwash material coming off of the mountain here. It's important to remember also that both of these mountains were capped by ice sheets in the last glacial maximum. So we have a lot of really flowy topography on the mountainsides. And then, so we see, bottom line, we see discontinuous faulting, stepping along the edge of the Boulder Mountain to the north. We see it again near the town of Bicknell, and then stepping out kind of further valleyward, just to the north of Bicknell. But he mapped the rest of the way, didn't find any more evidence of recent breaks that would be latest Pleistocene or younger along the Thousand Lake Fault. Okay, so how tall are these escarpments that he sees? So here, these are coming from the place that we looked at before, on the edge of Boulder Mountain, where the glacial deposits were coming over the top and debris flans. So he's done you can see some of the profiles that he's run and some of those outputs, and he finds displacements on the order of 1.4 to 1.6 meters and shows them here. This is using SCARP VS program. As you can see, it's discontinuous, but he tabulated all the displacements that he found, tried to kind of bin them within 5-kilometer sections along the escarpment and to see what the range of displacements were. So this is going from 0 is to the north, and 3,500 meters or 35 kilometers is to the south. And so we see escarpments for the first 5 kilometers, then the next 5 to 10. Then we don't have any escarpments for more than 5 kilometers. And then we see a bit of escarpments from about 18 to 32 kilometers. And so this shows the binning of those and how he estimated the mins, max, and medians of the displacements. And so he uses those to sum up the moments and estimate the magnitude of the rupture. So this table is showing that here. So most of the average displacements are on the order of just under a meter to just over a meter. The biggest displacements are around 2 meters or just over, and minimum displacements on the order of about 0.5 meter. And so gets mins and max of moment and estimates minimum moment magnitude and the maximum moment magnitude. And so he gets a moment magnitude of about 6.8 plus or minus 0.2. Okay, and then he compares this with just doing the Waskowski 2008 empirical relationship between moment magnitude and rupture length, given about 32 kilometer long rupture length, which shows a very good relationship, similar magnitude 6.8 earthquake. Okay, so in summary, Thousand Lake Fault has had 2 events in the last 61,000 years. So you could say this is about 30,000 years per event recurrence interval. The average occurrence event across the alluvial fan surface, assuming about 5 meters of total displacement, if we assume that each one is just over a meter, might suggest that we could have up to 4 events since that fan was abandoned, which we believe is about 120,000 years ago or so. That age comes from the all the OSL dates, as well as basically helium-3 dating of volcanic boulders strewn across the fan surface. Those are the youngest ages that come out. Of course, we do have some deposits that show as younger, but that could be just reworking things on the fan surface. But they could also be younger. It could be that it was active up to about 60,000 years ago. So given that range, we would expect a minimum recurrence of about 15,000 years per event and maximum about 30,000 years per event. So similar to what the trench data shows. And most likely recurrence data, if I was to put money on it, I would say is between 20 and 25,000 years per earthquake. If we look at the geologic slip rate and the average slip per event, that would suggest that we should have a much faster slip rate, right? We have 1 meter per event. If we pushed it up to 0.2 millimeters per year, that would suggest an earthquake every 4,000 years. We definitely don't see evidence for that. But on the low end of the geologic slip rate estimates, it gives us back to about 19,000 years per event, which is not too far out of the line of what we've seen in the recent past. The late Pleistocene slip rate does therefore align fairly well, although it would push it slightly lower than that minimum of the long-term geologic slip rate. It would say that we have about 4.4 to 4.8 meters in the last 60 to 120,000 years. And so that's 0.04 to 0.08 millimeters per year. So in summary, Thousand Lake Fault has a very low slip rate, but it has been active since the last glacial maximum, has a recurrence rate over the late Pleistocene to present of about 15 to 30,000 years between earthquakes. The most recent event, it ruptured about just over 30 kilometers, has a magnitude, which had a magnitude probably between 6.6 and 6.9. And I'll just add one other thing is some of those scarps that we see up on the top of the mountain look extremely fresh. And they may be being enhanced during wet years by almost like basically like periglacial soil creep processes along these steep escarpments up there. And so we saw evidence of this when we went up there this past year, where there was like basically soil creep going on right within the heart of the escarpment. This was not seen other visits to the site in other years, but definitely, and therefore it's not necessarily expressed in the LiDAR data that we saw, but it could be making the scarps look steeper than they actually are. Good question about whether or not they're increasing our estimated magnitude of displacement in some areas along the most recent event as well. But that's just one thing we recently noticed. It would be interesting to look at maybe historical imagery, try to look for some more evidence of recent creep and that magnitude of events, from magnitude of displacement from those sorts of creep events along these escarpments. Okay, so here's some reference, and thank you very much.